All right, good morning, everyone, or whichever time zone you are in. Greetings, and it's the first session of Thursday on solar ionosphere and scintillation, and the first talk is by Pietro Zucca, who will be talking about observations of Sun and Heliosphere with LOFAR. So all yours, Pietro, you can start now.
All right. So yeah, good morning, everybody. I guess that we will have also a wider audience following the recordings. So just in case that someone do not know me, I am Pietro Zucca, and I work at Astron in the Netherlands as a LOFAR telescope scientist with particular interest, of course, in solar physics and space weather. And I have the pleasure at the moment to chair the Solar and Space Weather KSP. So I will be presenting an overview of the work that we're doing together with the KSP members. Using the LOFAR telescope to study the Sun, but also the Heliosphere and the Ionosphere. So I'm going to start briefly with, I don't need to give an introduction to LOFAR, so I already removed that part, but I will start with, first of all, thanking the organizer for letting me be here and showing you this results. And then, of course, telling you about the observing modes and the observing campaign. So what are we doing? What time do we have available with LOFAR? What are we proposing to do? And just to let you know a little bit about the instrument as well, I will tell you about the difference between the different observing modes for the Sun and for the Heliosphere that are called the IIIb mode, but and of course also the interferometric mode. I will then give a very brief introduction of what's happening in the group about also the observation of the Heliosphere by using compact objects such as quasars and therefore interplanetary scintillation, but also pulsars. They can be used to extract the properties of the solar wind and transient, if any. So LOFAR, of course, everybody knows it's a very complex telescope. And these are the different key science projects, of course. So I will focus on the solar physics and space weather, a team of more than 40 people now. We have new PhD students from the different institutes. So it's really a pleasure to work with them. Now, the observing modes, what do we do? Because obviously observing the Sun, it's one thing, but observing the properties of the Heliosphere and the Ionosphere and different properties such as, the magnetic field or the density, you need different observing modes. So what we do is we try to maximize the time that we have available to perform simultaneous observation. We use the core station. So the central stations that are in the superturb at the center of the LOFAR telescope, an island about 300 meters, which contains the main 6 stations, but then also all the core stations around the superturb. So we're talking about baselines about 3 kilometers. We create, and these stations are in the same clock. So we can create what we call the tidal ray beams, so small pencil beams centered at the Sun and all around the Sun and the lower corona. But then at the same time, we use the core stations and the remote stations to observe and point a larger beam in interferometric mode. Of course, here we're talking about larger baselines, about 120 kilometers. At the same time, we use also the international stations. These are operated in fly-size mode, and they are pointing at quasars, very compact objects. Therefore, they twinkle with the solar wind and the plasma in the Heliosphere. And we can have a look at that, and also at pulsars, which are polarized, and therefore we can extract also Faraday rotation. I will tell you about the limitations, of course, and what's the status. But we point also at the Sun During important periods where instruments such as the Parker Solar Probe or Solar Orbiter are also very close to the sun, so that they can use and collaborate with the teams from the spacecraft to do remote sensing and in situ measurements. So it's a very complex scenario and which outputs an enormous amount of data sets. And I'm going to start to tell you about the solar observations, and then I will tell you about the others. Why did we bother about doing the tidal ray beam and the interferometric at the same time? Well, the reason is that we tried to extract the best of both from both modes. So the interferometric mode, of course, returns as a quality of the imaging, which is much better. We have the remote stations, so the resolution is at best. But it's limited about sorry, and the tidal ray beam, of course, are limited about just the core stations. So we can use baselines maximum to 3 kilometers. And of course, because you're reconstructing the image from this tidal ray, so the intensity of all these beams. So your image reconstruction, it depends also about the spacing of these beams. But the advantage of the tidal ray beam is, of course, the time resolution. You're talking about dynamic spectra in each of these beams, so you're talking about milliseconds for the resolution. And if you're tracking quasi-relativistic electrons that propagate at 0.6 C, then you like to have the best time resolution. Nevertheless, with interferometric mode, we managed to push the correlator to 0.16 seconds, which is actually not bad, and we're able to track also these quasi-relativistic beams. Now, just to give you an idea of the difference between these methods, with the tidal ray beam, we're limited in area. We can observe only, let's say, the lower corona due to the limited number of beams that you can put in concentric circles, let's say. So here I stretched really the color table in these three plots. You see the tidal ray beam, just to show you that outside we don't have any imaging. With interferometry, you have a very similar output for at least this radio burst. So when you have some radio burst, non-thermal emission, you can localize at the same time. Of course, you don't have the same sensitivity to understand the fine structures of this quiet sun, for example. When you add interferometry to with the remote stations, you can see that the source size, it's smaller, and you can see nicer feature of the radio emission itself. Nevertheless, we found that after 40 kilometers baseline, we don't have amplitudes anymore for several events. That means that the scatter and the enlargement, or the physical enlargement of the sources due to the corona itself, doesn't give us any smaller features. So we're concentrating everything more than 45 kilometers, let's say, to observe other important things like IPS, for example. So this gives us flexibility. One of the examples of using the remote stations for getting a better resolution comes here, for example, from when you have many solar radio bursts at the same time. This was a complex time, for example, in 2013, when you have different radio bursts, type 3s, type 2, and type 4. I will tell you a little bit later about what all of these are. But if you observe with LOFAR and remote baselines, at the time where this feature here, that it's called a moving type 4, this large broadband blob, we can resolve it with respect of the active region, which is still bright, where this type 3 happens. So you can see these two sources. And if you're looking at other instruments, such as the Nancy radioheliograph at the same frequency, which has baselines about 2 kilometers, you can see that you can't resolve the source. This is just a mosaic of the images to show you why do we really like to study the sun and the corona with LOFAR. Well, the reason is that it really extends our knowledge of the higher corona. So if you look here at the top panel, you can see the top panel images, you see some imaging of the sun from, a very high frequency, so 25 gigahertz with a new network of telescopes. They're not dedicated to the sun, but they're called the sun dish in Italy, Nobayama in Japan, etc. And you can see that when you go to lower frequency, you start losing details. But nevertheless, by adding the remote stations, you can still appreciate a lot of the details also of the quiet sun. And these are important, for example, when you want to study these parts, particularly, which is called corona hole. So parts where the solar wind here is faster and they're less bright here at low frequencies. By using this radio imaging, we're then able to start understanding better what's happening on, for example, the quiet sun. And I mentioned the quiet sun, a work that we're doing now with Peijin Zhang, a postdoc that is working now with us in the project, in the EU, under the EU project called Stellar. You can see here that we are really filling the gaps of the spectrum, the calibrated spectrum from the quiet sun. So you can see here the red points are covering the gap at low frequencies. And we are actually then trying to understand and matching with models for the emission of the quiet sun. We are also taking slices of the radio emission to understand what are the smallest details and resolution that we can obtain. Understanding also the size and the brightness temperature of the different regions. For example, in here, we're studying how the brightness temperatures of a coronal hole here are lower then, of course, the brighter regions. And these are very important measurements that we need also to constrain empirical model to understand what's happening higher up in the heliosphere for the solar wind, for example. And of course, we're also trying to investigate the size that we can obtain from LOFAR. Typically, we find that the north-south scan is smaller in size than the east-west, as the east-west in the equatorial region is the radio emission is larger. It extends more into outside the sun. Just quickly in view of time, I tell you, why do we investigate all of these different features that appear in the dynamic spectra? Well, the reason is because this, they're telling basically a story on what's happening on the sun, what's happening during a solar eruption. When we have electron beams that are escaping outside, we can see features such as the type 3s, which are these very fast drifting features. But when we have shocks, when you have a front plasma, a magnetized plasma that is moving faster than the magnetosonic speed, you then generate a shock, and you can observe it like this type 2 radio burst, these lanes of emission. They can tell you a lot about what, the kinematic, for example, of the shock. But when we have trapped electrons that are still glowing after a flare, we have what I showed before, this type 4, this broadband emission that often can also be drifting, a drifting type 4, as the anchored position of the magnetic field inside the CME then is stretched by the propagation of the CME itself. And of course, with LOFAR, we can observe the imaging higher up. And this is where the region of the magnetic fields after 2.5 solar radii are mostly propagating radial. And that tells you a lot on how the particles then can propagate outside in the heliosphere. So it's very important to understand where the acceleration of the particles that's happening higher up in the corona. An example of the imaging that we can obtain with such complex event and the variety of, you have here a type 3, it's happening now, but then at the same time you have a noise storm. All of these bursts are happening here. It's a noisy storm that it's there all the time. Here it's happening, the type 2 is happening, some shock region here, but at the same time this moving type 4, this blob of broadband emission is starting to rise here. You see now all the frequency are concentric, all in the same region, and the emission rises up. Here you're losing the type 4, so it goes back to the active region, but the emission here continues to rise. So you have the source from here up to here. You can infer many characteristics of course of the radio burst, not only characteristic of the kinematics, but also the fine features inside the radio burst itself. So what else we can do? Well, we can understand also about the properties on how the radio emission escapes the corona. And here you have an example in what we call the type 3b pair. It's a type 3, so electron beams, again, propagating outside. This is plasma emission. The emission is proportional to the frequency that you observe is proportional to the square root of the electron density. And what we see is that the fundamental emission, being very close to the plasma emission itself, the medium there is not completely transparent, it's not optically thin, so you have just patchy emission that comes out. But not only in the dynamic spectra, but also in the imaging. At this point, the emission is very erratic, while at this time where you have the harmonic, you can follow much better the kinematics. So here is an example. You have the fundamental emission, which is enlarged due to the fact that you are close to the plasma frequency at which this is the exact frequency that you're observing in the plasma. So it doesn't escape freely. And so we can follow the kinematics from the harmonic quite well. Other important things that we're doing in the team is to use the UV plane and the visibilities to fit directly in this space the sizes of the sources, to understand what's the limitation of the sources that we can observe. Other studies are about the shock signatures, such as type 2 radio burst, the one that I showed you before, lanes of emission, where particles are continually accelerated at the shock front. Now here, there is a nice paper from Yasmina Magdalenic that showed all of this fine structure zooming in this complex radio bursts. This is quite a dated paper now in 2018, but I just wanted to show you how one interest is also to understand CMEs and how these are being ejected out of the sun. Here is the radio emission location. You can see that it's located in a position where we have this the modeling of the CME. You can see the Mach number, it's higher here because there is a dense streamer. There is a dense streamer, and therefore the alpha in speed there becomes lower. And you can see how these parameters, the speed of the CME itself, but also the angle at which the magnetic field is oriented with respect of the perpendicular of the shock of the front, it's very important. We find, in fact, that just in regions that are called quasi-perpendicular, you can get the radio emission. You get the conditions for the particles to be accelerated and then Langmuir waves to form and decay into radio waves. Follow-up studies in this type 2 radio burst are again by Kira Maguire, working in Ireland, in Dublin, with Professor Peter Gallagher. And you can see here how Kira did a detailed analysis on how this radio bursts are and the shape of the radio burst are related also to the jet and the plasma emission signature that you see, the sun. Now, of course, we're not observing only the sun and the radio burst, and of course the quiet sun, understanding how the quiet sun works. But we observe also the heliosphere, as I mentioned before, with different techniques. So here is just to tell you about, we use radio imaging, radio triangulation from the spacecraft such as Parker Solar Probe and others to then track these electron beams. This is a LOFAR imaging. You can see the electron beams propagating out, but then you also see it after the ionospheric cutoff, below 10 megahertz, you can see from spacecraft, of course. And by using the triangulation, we're able to see where the position is coming with triangulating the emission with Parker Solar Probe and WIND, another satellite at the Lagrangian point 1 from Earth and Sun. And you can see then that you want to understand the connection from what we observe with LOFAR at the low corona and what we observe with the satellites in the higher corona. Similar studies are ongoing, and you can see how, for example, here, this is a beautiful plot that was produced by Vratislav Kruper. And you see how in the PSP, the Parker Solar Probe, we're about 7 minutes earlier than the others. This is due to the fact that PSP is very close to the sun. So you can observe the type 3 before. So it's quite funny to see this displacement on the PSP type 3. And so again, other studies that really triangulate the source with LOFAR and then higher up with the Parker Solar Probe. So really to understand how the magnetic field structure and also track the radio burst from the low corona to the heliosphere.
Pietro, you have 4 minutes.
4 minutes, fantastic. That's exactly enough to tell you about the other studies in the heliosphere, which are the interplanetary scintillation. So as I mentioned before, we are using the international stations to point at quasars, very compact sources. They start twinkling the fall, same as when we see star twinkling in our ionosphere, in our atmosphere. So when you observe at different baselines, you're observing, say, in the station in Poland, and then in the station in Ireland, you have a baseline of about 1,400 kilometers, and you see some pattern of the scintillation in one baseline, and then after a certain time, you see it somewhere else. You know the baseline, and therefore you obtain with the cross correlation a speed of the plasma. Now imagine to do it with a lot of sources. But you can do it two times in 2 ways. You observe one source, but you observe it for a very long time, such as what Richard did here for the passage of a CME in May 2015. You observe a quasar for a very long time, and you stare at the quasars and you understand if a dense source is passing in front of it. Or you can observe many sources, and with all the line of sight that you obtain, you do what is called the tomography. So you can obtain an understanding of what's happening in the solar wind by directly measuring the scintillation. Other important studies are, of course, the study of Pulsar, which Caterina will tell you later in this conference. So I will just go briefly to tell that using this characteristic that is called a dispersion measure, you can obtain results about the density of the solar wind as the pulsar approaches the sun and then goes far again from it. So you see the difference in density. But what Caterina and the team is doing, and I'm sure they're going to tell you later, is also comparing with modeling of the heliosphere with models such as it's called the EUHFORIA. It's a model that tells us about the features in the heliosphere. So they are comparing about what they're observing there. These are some promising results from Mario Bisi et al., where they see an increase on the rotation measure and dispersion measure while a CME was passing in the line of sight. And of course, the Faraday rotation is very important because it's going to tell us about the magnetic field of the CME itself. Other studies are using modeling of the CME in 3D to really understand what's happening in the line of sight that we're looking with pulsars. I finish with the last 30 seconds telling also about the studies of the ionosphere. The team is also busy in understanding the scintillation index in the ionosphere with such a unprecedented resolution. When you look at objects like Casei, for example, again, you can see how they scintillate at low frequencies, and you can observe the pattern of the scintillation on top of all the stations, and therefore understanding how the ionosphere is behaving. The ultimate thing for the last 20 seconds is about a project that we're now putting together with the KSP is to continue the LOFAR4 space weather project. So to propose to use a single station of LOFAR to test some of the monitoring of the sun in real time. And that is all I had to say. Thank you very much.
Thank you, Pietro, for a very comprehensive overview of the solar physics and showing some of the most beautiful images I have seen of sun with LOFAR. So thank you. And I'll please raise your hand and ask questions. And Ashley, please. Oh, I thought I saw Ashley's hands up. Joe, please ask your question.
Yeah, I think Ashley was just applauding. Pietro, really lovely talk. I just had a quick question. You didn't like amazing data set, but you didn't mention polarization properties, and this really helps with differentiating between plasma and ECMI from these types of emissions. I'm just wondering, have you tried to recover some of that stuff, particularly circular polarization in these different data sets and what they can tell you?
Yeah, absolutely. Very good question, Joe. This is one of I didn't show this work. There is a recent work from Diana Morrison et al., which is now is under review, where we started from the tidal ray beam. So by using the different Stokes parameter, RQ, UV, and retrieving the degree of circular polarization, we have some problems instrumentally where you have spilling from Stokes V to Stokes Q, and you have in secondary order of spilling from Stokes I to V. So it's really difficult at the moment to obtain a very good result, but we're working, and I think the paper from Diana will be probably accepted soon. But that is from the tidal ray beam, so from the dynamic spectra itself. What we're trying to do is now to calibrate the image with prefactor. So we're trying with Tim, Pegin, and Alexander Drabant to run all the steps of prefactor. And as you know, there you have also the Faraday rotation calibration. So once we achieve that, we can have a better estimation of the polarization. At the moment, we can have it, but with a very high error bar, but it's still enough. It's still enough to see the polarization, for example, from.
Yeah, I was about to say, what kind of polarization percentages are you measuring? You know, because like, yeah, if you're only measuring a few percent, I believe it, but if you're measuring tens of percent, you
exactly. So because we're measuring tens of percent, 20 or more, then it's a little bit easier to
just with large uncertainty. Well, that's cool. No, that's really awesome, Pietro.
Thanks, Joe. Stefan, please ask your question.
Hi, nice talk, Pietro. Have you seen enough type 4 bursts to say whether or not there are stationary type 4 bursts, or do all of them look as if they're moving?
We didn't see extensive amount of type 4, but we did observe a number like that fits in one hand, so about 5, let's say. And from what we see, there are some that look more stationary, but the one that we have in detail, they are moving type 4s, and you can see it from the dynamic spectra already clearly. But from the imaging is striking how all this broadband emission is then shifting higher up. So I cannot extract statistics yet, of course, but there are papers about the statistics between the moving and the stationary type 4. But what we observe some moving and some stationary.
Okay, thanks.
Thanks.
Thanks, Stefan. Any more question for Pietro? All right. If not now, I would encourage you to please continue discussing about it on Slack channel as well as the Gather Town. And thanks, Pietro, again for a very, very nice talk. It was a very comprehensive overview. Thank you very much. So the next talk is by Kate Ross, and Kate will be talking about a very scintillating result, and I did not want to steal the thunder. So we'll let Kate talk about her result. Thanks.
Thank you so much. And thank you to the organizers for giving me this talk. I'm really excited to present some of these results. Just calling in from Wajak Noongar Budja, which is Perth in Western Australia. And I'll start by saying I gave a bit of an introduction to myself on the Slack where I made some promises about this talk. So to preface this, I will be addressing all of these. In this talk, we'll be talking about baby AGN and frustrated teens, as well as some variability with two telescopes, MWA and ATCA, and in particular, looking at detecting intraday variability using these telescopes. But I will also touch on one of the most important discoveries of my PhD as well. So I will hopefully meet all that criteria as well. So to get started, this talk is about spectral variability. So I want to talk about the things that I want to see varying spectrally. So to start off, peak spectrum sources, they're around 10% of AGN show that they have this peak in their SED, as you can see on the right there from Joe Callaghan's paper. And this peak, it's debated where it comes from, but we see that they all have a very typical morphology of classic AGN, but on much smaller scales. So they still have the core and jet and lobes, but typically on scales of around 20 kiloparsecs max. So the reason behind this curvature or this turnover is still debated. We see this absorption probably because of two scenarios. Firstly, that these are frustrated sources, or they're surrounded by this dense cloud that's causing free absorption, or that they're really young sources, and that's also why they're so compact. And then we're seeing synchrotron self-absorption. Unfortunately, being able to tell the difference between these two scenarios is really quite difficult, because you need to have sufficient sampling below the spectral turnover, and also a lot of the spectral modeling kind of just comes back saying both are appropriate. So it's been a big question in determining what's going on with these peak spectrum sources, and it's definitely a big field that's sort of up and coming. And if you want to see some information about that, I recommend seeing the ODEA review from last year. It really covers pretty much everything. So spectral variability, why are we interested in spectra? Well, I mean, I just mentioned that peak spectrum sources are really interesting, but you can actually tell a lot of information about the source itself from its history, its energetics, and trying to get duty cycles of AGN. So really understanding the evolution of galaxies and AGN in particular. But a lot of that is really crucial to actually having the spectral information. And in fact, I want to make a mention of yesterday's talk from Leah, who mentioned a lot of really interesting stuff about getting this small scale structure of sources via high resolution imaging. And in fact, we can get a lot of that high resolution information from spectra as well, provided you have really high quality spectra. So getting all this information and understanding of the history of AGN, you're really limited by how well your spectra is sampled, and also the quality of that spectra. So moving on to the next part of spectral variability is the variability side of things. And there again, two main sort of categories, either intrinsic relating to the source itself, or extrinsic where the light is varied on the path to observation. So intrinsic can tell you a lot about, again, the source itself, whether it's evolving on these timescales, or whether we're seeing these sort of shocks or big events that are happening within the source itself. We can also see changes in the optical depth sort of just surrounding the source, causing that variability at low frequency. Whereas extrinsic, we're looking at scintillation. So thanks to Pietro, who introduced that really well. And interplanetary scintillation, I won't go into too much detail because John's giving a talk in this session later. I will mention that interstellar scintillation, where we're seeing twinkling because of the interstellar medium in the Milky Way, comes in a few different forms: refractive, diffractive, and weak. And that's based on what your observational frequency is, and they can actually show up creating different spectral effects as well. But again, if you want to find this information of either the source or the medium in between, you're really limited by how much spectral and temporal coverage you have. I kind of hinted there that the scintillation produces these different spectral effects, but if you're not sampling that spectra enough, you're really not going to see it. And likewise, if you don't have enough temporal coverage, then you really can't estimate your timescales appropriately. So it's also pretty much impossible to be able to tell the difference between intrinsic and extrinsic if you don't sample the temporal or spectral coverage well either. So that's really important for being able to figure out what's causing variability. In terms of previous studies of variability, a lot of it has been limited to either single frequencies, higher frequencies, or smaller populations. And largely that comes down to simply not having technology available. Telescopes simply weren't able to sample or survey the sky with lots of spectral coverage, quite quickly. So when it was first discovered back in 1972 by Richard Hunstead, it was sort of a weird discovery to see variability at around 400 megahertz. But later we sort of figured out that that was likely due to scintillation. And since then, there's been big surveys of lots of sources to try and get an understanding of the population at whole, but again, limited to a single frequency. So for example, the MWA transient survey by Martin Bell in 2019. There's also work done at higher frequencies. In particular, Christina Nyland's work recently last year was really interesting at finding this variability and changing AGN that were changing the way that they looked, or going from radio loud to radio quiet. So we see quite dynamic effects on observable timescales at higher frequencies, but that's sort of expected because you're probing closer into the AGN itself. At really low frequencies, so in the megahertz regime, you're probing that extended structure, so the lobes and sort of that diffuse emission. I do want to point out a particular survey study done by Stephen Tingay in 2015. You can see here on the right, this SED of a peak spectrum source is quite variable, but it's really particularly interesting below the spectral turnover here, where we can see these different mechanisms and different spectral models, but without the sufficient sampling in this regime, it's really hard to pin down what's actually causing that variability. It's also worth noting that in this paper, they found there was different causes of variability for above and below the turnover. So having that spectral coverage in the different regimes of optically thin and optically thick is really crucial for being able to figure out what's causing the variability in those different areas as well. So that brings me to my first paper from last year, where we did a survey with the MWA using the galactic and extragalactic full sky MWA survey, or the GLEAM survey, in particular the South Galactic Pole region done by Tom Franzen. So we surveyed over 20,000 sources and had a spectral coverage of around 130 megahertz with 16 individual flux density measurements. So we had quite a large fractional bandwidth as well. From this, we had two different epochs split about a year apart. And in order to figure out what was going on, it's really no longer appropriate with this sort of survey to kind of go through 20,000 individual SEDs being like, yes, variable, no variable, which was a lot of the strategies of previous big surveys. So we kind of needed to come up with a way to extract variability using statistics. So that was a big part of this paper. And there were two main statistics, and it was figuring out both whether or not it's actually variable, but then also the type of variability as well. So the VIP, or the variable index parameter, measures whether or not a source is showing a significant change in the following year of observation. And the MOS, the measure of spectral shape, is seeing if the change, the variability causes a change in the spectral shape as well. And in fact, when we employed those statistics, we found over 300 sources that were showing variability in the megahertz regime on just a year-long timescale, and 50 of those were showing a dramatic change in their spectral shape in just 1 year, which is really pretty unexpected. The most interesting thing, I think, is that the ones that were changing their spectral shape are really inconsistent with interstellar scintillation, which shows a sort of broadband effect at megahertz frequencies. So what's going on to cause these ones to change their shape in just 1 year? And also really interestingly, we found that peak spectrum sources are intrinsically more variable than typical AGN. So what's next? Well, this is where it gets exciting. So we're doing a follow-up at the moment with the aim to study a sample of these variable sources, but having a larger, more time cadences and a larger spectral coverage as well. So using the MWA and the ACCA, we look to get simultaneous spectral coverage from 70 megahertz up to 10 gigahertz with 6 different epochs around on a year time scale. And we chose 15 peak spectrum sources for the survey. Unfortunately, as most observational astronomers will be aware, your observations don't necessarily go to plan. So we actually only got 2 simultaneous observations between the MWA and the ACCA. And I've put a star next to April and May for the MWA because I actually made a pretty huge discovery. In some of my images, I found this source that was really large, very resolved, and as you can see in this image, causing quite an effect to the rest of the image as well. And this was quite puzzling for a while until we realized it was actually just the sun. So unfortunately for 2 of my observations for MWA in April and May, they were daytime observations. So sometimes we had to discard those observations for some sources. So in the end, we ended up with only 2 epochs with simultaneous MWA and ACCA observations. But it's interesting that we now are sampling 4 different cadences for the MWA. So we've got month-long observations across the 6-month time cadence and also 1 year and 6 years between our original study in 2013 and 14 and now. So what do we see? Well, in the ACCA on timescales of months, we saw no significant variability in the gigahertz regime, but in the megahertz regime, we really saw quite a lot going on. There's month-to-month variability, and again, like in the first paper, we see different types of variability as well. So not only are there sources that seem to just shift up and down, as we saw in the first paper, but we see sources that change their spectral shape. They have a variable peak frequency and really are just showing some interesting behavior. For this talk, I'm going to be focusing on 2 particularly interesting sources, but if you're interested in seeing the rest, stay tuned for the paper where you can see the full results. So firstly, having a look at Gleam J001513. In this one, you can see there's sort of nothing going on too dramatically in the gigahertz regime. There's a bit more noise going on with the X band, but unfortunately nothing that we can really conclusively say was variability. In the megahertz regime, it looks like there's sort of a general trend of getting slightly brighter in the 2020 observations, and overall it seems to have kept its peak spectrum shape pretty consistently. So what's going on? It could be that this is interstellar scintillation, and if that's the case, what would we expect? So let's have a look at interstellar scintillation in a bit more detail. Firstly, there's, as I mentioned earlier, a few different regimes. If we're looking at frequencies below 8 gigahertz, we're in a strong regime where there's refractive and diffractive scintillation. I've only put in bold there refractive because diffractive scintillation has a really short bandwidth. And so to see smooth SEDs is really inconsistent with diffractive scintillation. So we can rule that one out at least. In refractive timescale, refractive scintillation, we're looking at timescales in the megahertz regime of around 1.5 years, whereas just 5 hours for the 5 gigahertz. We're also looking at modulation indices of around 0.1 to 0.8, so more modulation at the higher frequencies as it gets closer to that transition frequency. And likewise, we're looking at spatial scales of milliarcseconds to microarcseconds. In the megahertz regime, that is a larger spatial scale, but you can really probe very small structures with scintillation at gigahertz frequencies. And likewise, in the weak regime, so above the transition frequency of 8 gigahertz, we're looking at even shorter timescales of about 2 hours and even larger modulation and even smaller spatial scales as well. So if we can find this scintillation at the gigahertz frequencies, we can be getting this really small scale structure of sources. However, the gigahertz is showing scintillation on timescales of hours. So in our observations over the months, we're actually averaging over that. So we took some follow-up observations of J001513 with the ACCA at 5 and 9, and we actually see a small scale modulation going on there. Obviously, we only have 2 epochs here or 2 time sampling, so it's a little hard to say what the time scale is and also what the modulation is, but it does seem to be suggesting that there is intraday variability for this source, which is really exciting that we just happen to have found this by looking for variability first at the megahertz regime and then searching for it at shorter timescales in gigahertz regime. So it could be ISS. That pretty much is everything we see is really consistent with that. We found the interstellar scintillation at gigahertz frequencies that is consistent with that scintillation, what we expect for that. And also at megahertz frequencies, we're sampling about a year timescale, and we're seeing that slow increase in flux density across the entire MWA band. So this is entirely consistent with interstellar scintillation, and we can pretty much be chuffed with that result, I think. So my second, I actually do want to touch on another really good example. This one here, you can see in October, it's gotten slightly fainter, just slowly decreasing but has really kept that spectral shape pretty much exactly the same across the whole time. So another potential candidate for showing intraday variability with the ACPA as well, and hopefully we can follow that up and confirm that as well. So the other source I wanted to focus on today is this one here. You can see the variability is quite different to what we saw with the J001513. In particular, there's quite a dramatic shape change in October 2020. And let's zoom in on the MWA. You can see here there's a little bit going on, and more or less the peak frequency is fairly consistent until we get to October, where things get a little bit wild. So having a closer look, we see no gigahertz variability again. And overall, there's a slow decreasing flux density across the MWA until we get to October, when there's really quite a dramatic change, not only in the spectral shape, but the peak frequency as well. So could this be interstellar scintillation? Well, it could also be changes in the synchrotron self-absorption, and it could also be changes in the free absorption. So if we first look at interstellar scintillation.
That you have 2 minutes.
Thank you. We followed this up the same time with J001513, and you can see in comparison, there's really nothing going on. So we don't see too much with interstellar scintillation. Let's rule that one out for now. In terms of changing synchrotron self-absorption, the increase in peak frequency in October is consistent with a contraction of source size, which is really quite unphysical. So we can also rule out changes in synchrotron self-absorption. In terms of changes in free absorption, well, if we run some spectral modeling on the October epoch in particular, the only model that can consistently fit it is an inhomogeneous free absorption model. And so that's also really consistent with what we see in terms of the variability as well. So it looks like we're now seeing variability due to the changes in the free absorption, which means we can also actually understand what's causing the turnover for this source, because it's unlikely that that would be changing on these timescales as well. So I also want to point out this source here quickly, which seems to show a similar effect. So unlike J020507, which saw an increase in absorption, so consistent with a denser medium or a hotter medium, this one here shows less absorption, consistent with a less dense medium or a cooler medium. So just to conclude, and hopefully I've met all the criteria that I said I would, talked about young AGN and frustrated teens that show spectral variability and seem to be a unique population where we can understand different regimes of variability, and they're really quite an interesting population. And spectral variability itself seems to be a really interesting tool for getting this really small scale structure of sources, and on the scales of microarcseconds to milliarcseconds, but it's also the one that can help us determine what's causing absorption of peak spectrum sources, and in ways that would otherwise be too expensive to get that spectral sampling or high resolution images. And we've also got a new method for detecting intraday variability, which is really promising as well. And lastly, the biggest discovery for life, well, I discovered the sun. Unfortunately, it was not what I wanted to find, but it's exciting to know that it's still there. So thank you so much.
Thank you, Kat, for a very nice talk. And let me thank on behalf of all of us. And let's take questions for Kat. And the first question is by Ashley. Oh, sorry, Christina, sorry.
Hi, Kat. That was a really fantastic talk. Really exciting stuff. Free absorption, that's really cool. I'm just curious, have you had a chance to look into the properties of the host of the sources that may have FFA? Are they dusty? Are they red? Those kind of things.
Not yet. We did actually get some WIFE observations for a couple of these sources to get the spectra. Unfortunately, it was cloudy. And also, unfortunately, I chose the sources before seeing this really interesting result. October was the last epoch that I found, and that was where all the change happened. So unfortunately, I chose sources that were less interesting for that. And J020507 is particularly faint, so I haven't been able to get a spectra to get that information, but it is something that will be really interesting. Yeah.
Thanks so much.
Thank you. Ashley, please go ahead and ask your question.
Hi, yeah, thank you for the talk. I guess I'm wondering, there was, a big gap in frequency coverage, like sort of 300 megahertz to 1 gigahertz. And I was wondering if there's value in trying to pursue that sort of frequency range, or is it more important to do the very low and the very high?
That's a really good question. Ideally, I think it would be ideal to have the full coverage, but obviously sometimes that's really hard to achieve. I think what this study has really shown is that identifying the variability at megahertz frequencies can be really useful, because with new telescopes like MWA coming online and heading into the SK era, we can survey the sky quite quickly and get that sort of first pass variability. And then I think following up at those higher frequencies from 1 gigahertz up to much higher would be really great. In particular, it's definitely useful. I shouldn't be writing it off. It's really useful for actually sampling the turnover as well. So you can see in this one, even in this gap here, the peak frequency, it can be hard to know exactly where it is. And same with, this one here in October. Oh, keep going back. In October, it's very hard to see where the actual turnover is. Like maybe it's starting to go here, but if we had that full spectral coverage, we can actually sample that turnover quite well. And if you see how the flux density changes at the peak, as well as if it changes frequency, that can also tell you a lot about what's causing the variability. So I would love to get spectral coverage there for sure. Yeah.
All right, thanks, Kat, and thank you for a very nice talk. And I would encourage all of you to continue the discussion over Slack and GatherTown. And our next speaker probably is not around.
Yeah, I would just move on to Frits. Thanks.
Right. So let's go to Frits Sweijen's talk on sub-arcsecond widefield imaging with LOFAR.
All right, give me a second to share my screen. Share screen should be this one. Are there some slides showing now?
Yes, perfect.
Yes. Okay, so hello everybody. Good morning, good evening, good afternoon, wherever you are. I'm Frits. I'm a PhD candidate at Leiden Observatory. And first of all, thank you to the organizers for allowing me to show a little bit of what I've been doing the last couple of years, and also a lot of thanks to my collaborators, without whom this work would not have been possible. So tonight, a bit of a change of gears, I guess. I'll be talking about widefield sub-arcsecond imaging with LOFAR. It is related to the ionosphere, so in that regard, we are in the right session. And this is about a paper that has recently been accepted into Nature Astronomy. So as per their guidelines, I would like to ask you to not share any of this with any publicly facing thing. So let's get into it. For more about LOFAR in general and high-resolution imaging, I refer back to Leia's talk from session 7. So I'll give a short introduction why we care about the wide field aspects of things, and then I'll move on to the calibration and imaging, how we tackled this aspect of the LOFAR telescope. Of course, I will show some results, and I will finish off with some concluding remarks. And on the right, we can see a few group pictures of the members of the Long Baseline Working Group who've helped a lot over the time. Before we jump into things, I'd like to reflect on this image, and this has really become one of my favorite radio images of the last time. And the reason that I like this image so much is because it's almost the polar opposite of what I'm talking about tonight. And this is very early radio data taken by Jansky and then plotted into a more familiar format. And the reason that I like this image is if you look at the bottom right where the resolution is indicated, we're talking about a resolution of 36 degrees by 24 degrees. And those are just numbers that we're not really used to seeing anymore, especially not in terms of resolution. So jumping straight onto it, I'm obligated to show the LOFAR telescope. I think most of you will be familiar with it, so I won't dwell on this too long. I will only note that we are using the HBA frequency range, so between 120 and 168 megahertz. And we have these beautiful international baselines that offer us lengths of up to 2,000 kilometers, with which we can come down to 0.3 arcseconds angular resolution. And we have a large field of view of 2.5 degrees that we aim to exploit at that resolution. So the question is, why do we even care about this high-resolution wide-field imaging aspect? And for me, the most important reason is that 90% of lots remains unresolved. So that means a 6 arcsecond resolution is simply not enough, and we should take a look at what's in there. And even the sources that you might classify as resolved in terms of it has multiple beams across it and you can see some structure in there, it will still benefit you if you get this jump in resolution. So what we see here is a source 4C4315. This is a high redshift radio galaxy that I studied at the start of my PhD. And you can see that with the Dutch LOFAR telescope, we can derive that there's an AGN here probably. There's probably some double lobe structure, but that's about where it all ends. But if you look at the same source with the International LOFAR telescope, then you can see this beautiful FR2-like radio structure. We can see a core, we can see the hotspots and the lobes, and suddenly a whole new world opens, proverbially speaking. So as a naive PhD student, I said, well, let's move on from one source to everything. And with everything in this case, I mean everything within the primary beam. And not knowing what I was getting myself into, I set out on this journey. So as with any radio image, this problem was split into two different sides. On the one hand, you have the calibration issues, and on the other hand, you have the imaging issues. And for calibration, we first had to assess whether the direction-independent calibration that we are doing, I will elaborate on all of this in a moment, was generally valid. So would we even be able to get away with direction-dependent calibration? And secondly, the question was, can we do this direction-dependent calibration in the first place, which would depend on how many sources we would expect to detect at sub-arcsecond resolution and how many of those sources would retain enough compact flux and source structure to calibrate on. And on the other hand, the imaging is slightly problematic because imaging the full field of view at this resolution requires quite a significant image size. We need roughly 10 gigapixels to cover the entire field of view. And computationally, that means that a single high-resolution sub-arcsecond image with LOFAR of the entire field of view is equivalent to 25 normal lots pointings. So it's not exactly cheap to do either. So as we all know here, probably the biggest enemy we have when imaging the radio sky is the sky itself. So what this animation shows us is on the left a calm ionosphere and on the right a slightly wilder ionosphere. And the reason I'm showing this is that these images have a resolution of around 3 arc minutes. And you can see that if the ionosphere really decides to go and bother you, that it can create disturbances over arc minute scales. And effectively, we need to correct this down all the way to sub-arcsecond scales on the sky. Now, luckily, a lot of the road has already been paved for me. So Leah talked about her LOFAR VLBI pipeline and the long baseline calibrator survey, which helped immensely because this forms the basis of the direction-independent calibration. And these long baseline calibrator sources, they are very bright, and that means that we can self-calibrate on them relatively easily, actually. Now, usually if you say VLBI and self-calibration in the same sentence, I get the feeling that people are at least a little bit suspicious of what you're doing. But with LOFAR, the UV coverage is dense enough that this is actually pretty safe to do, and you are actually even fairly robust against a completely wrong input model. So on the right, you can see the LBCS source that I used for this observation. And I gave it an input model of a point source because I simply didn't know what it was. And you can see that in the bottom image, after a few rounds of self-calibration, we arrive at a believable source structure. And with this calibration, we take care of any clock offsets between stations, and we also correct for the bulk of the ionosphere. But there's one catch to using these LBCS sources, and that is they are bright, which is a good thing. They're typically 100 millijanskys or more in terms of compact flux, but they're also very rare. And on average, you find 1, maybe 2 per square degrees. And the ionosphere can vary much more rapidly in terms of spatial scales. So these sources are not going to cut it for the direction-dependent calibration that we would need if we want to calibrate the entire field of view. So in order to extend the calibration to direction-dependent effects, we took a slightly different approach where we first made an intermediate resolution image. And the reason for that is that judging the amount of compact flux in sources from 6 arcseconds to 0.3 arcseconds is quite difficult. Even a relatively bright 6 arcsecond source doesn't necessarily need to stay compact all the way down to 0.3 arcseconds. So the idea was if we make a 1 arcsecond image, then we would have a better idea of what remains compact all the way down to the full native resolution. And so what we did is we ran a source finder on this intermediate resolution image, and then we selected a bunch of candidate calibrators based on their peak intensities. And we did this in 2 rounds. We started conservatively at 50 millijansky per beam intensity, and it turned out we could go 1 step fainter, and then we chose 25 millijanskys per beam as our intensity cut for these calibrator candidates. And that yielded us a list of 46 candidates, of which in the end 44 survived the direction-dependent calibration. And on the right, you can see the distribution of these sources across the field. So these are not special sources by any means. They're just arbitrary field sources. And you can see that we actually have quite an even coverage over the entire field. So that seems promising. And the green square that you see in this image is the location of the LBCS source that was used for the direction-independent calibration. Now, as you can already see by the peak intensities, these field sources are way fainter than these bright Jansky class LBCS sources. But luckily, there was one more thing that we could leverage in this calibration, and that is that we're really only solving for a differential ionospheric effect at this point. So instead of now having to solve for visibility phases as function of both time and frequency, we can constrain all of them using this equation that you see here, which basically tells you that if you're dominated by the ionosphere, your phases should follow some physical constant multiplied by the ratio of the electron density divided by your observing frequency. Now we know the observing frequency because we built a telescope. So the only thing that we need to determine is this d-tech value. And this increases our effective signal to noise tremendously because now it means we only have one phase solution per time slot using the entire bandwidth to constrain it. And so we did this for all of those sources that I mentioned before. We ran this calibration, and it worked quite well, actually, on a variety of different morphologies. So on the left, you can see here 3 examples of these arbitrary sources, all the way from a very compact point source to a very diffuse-looking radio galaxy. And in the columns, you can see on the left the initial image of what we got when you only applied the direction-independent calibration. So the calibration from the source in the green square, which is actually already quite good. I didn't expect it to look that coherent, to be honest. But you can still see these massive spikes surrounding these sources that indicate there are still quite significant ionospheric distortions remaining. And then in the second column, once you solve for that effect, you can see these spikes clear up nicely and the source quality increases. And then finally, we also did a very slow, long time scale amplitude solve to clean up any remaining slowly varying amplitude problems around the sources. And so you can see that we can calibrate basically all of these sources to a very nice quality all across the field. And we can take this one step further because now we have this 44 discrete directions in which we have corrections. So in principle, we could follow a sort of facet-based approach where for every, you do some Voronoi tessellation or something, and then for every region of the sky, you apply the solution of the nearest calibrator. But because we have this relatively dense grid of points, we can also interpolate these and determine solutions for every pixel in the field. And small sensitivity warning if you're sensitive to flashing colors or something, then look away for the next slide. But if you do that and you interpolate all these solutions, then you get something like this. And what I'm showing here is sort of the inverse of the movie I showed earlier of the ionosphere moving stuff around. What we see here is on the left for a German station and on the right for the Irish station, the variation of this ionosphere for that station. And you can see that it can vary sometimes quite rapidly and sometimes it's a little bit calmer. And as expected, the variations on the Irish station are also a lot wilder than the German station because the baselines with the Irish station tend to be longer. They look through more of the ionosphere. And they ignore everything outside of the black circle, which indicates the field of view. And so now that we have a correction for basically every pixel in our image, we still had to make this image, which was kind of a problem because once we wanted to do that, we realized we would need a image the size of about 100,000 by 100,000 pixels. And if you ask WSClean or CASA or whatever your favorite imager is to do that, it will just say no, or your computer will spontaneously combust if you try and force it to. So we had to split this up into multiple smaller images, and we settled on a 5x5 grid following a sort of facet-based approach where each of these images was processed separately and then later stitched back together to make one large image. And we did this in combination with WSClean in combination with a recently developed image domain gridder. And this image domain gridding algorithm can efficiently apply the solutions that I described earlier in the previous slides during the gridding process itself, which allows for these nice corrections for every location in the field. And just to give an indication on how intensive this was for the people that this means something to, the entire imaging part took about 190,000 core hours. And if you use the hardware that I've listed here, then you should count on anywhere roughly from 3 to 7 days per each of these facets that are shown on the left. So you really want to throw a lot of compute nodes against this. And ideally, you want to have one computer per every image that you need to make. And as I said in the beginning, effectively, to make this entire 5x5 grid, we're doing the same amount of work as LOTS would need for one pointing. So it's still very expensive to do this. But luckily, the results were positive, and I can at least conclude that full field of view imaging with the ILT is doable, although expensive. And we ended up with a 7 gigapixel image covering 6.6 square degrees over the sky. And something that I found like a nice thing to know is that this is 1/6 of the total amount of pixels in the entire first survey. So that gives us a sense of scale of what's going on here. And the image on the right gives a sort of artistic overview of what we've imaged on the sky, where the major square in the center gives the 6 arcsecond image of the area that we've covered and the moon for scale. And then the insets around the edge show a variety of 0.3 arcsecond sources that we've detected across the field, chosen for their nice morphologies.
You have 2 minutes left.
I have 2 minutes, perfect. And if you sum this up in some numbers, comparing this with LOTS, so LOTS has a 6x6 arcsecond resolution. It reaches a depth of around 70 microjensky per beam. And in the area that we've covered, we detect 5,650 sources. Now, if you move to the high resolution version of that same image, then we reach a resolution of 0.3 by 0.4 arcseconds and a sensitivity of approximately 25 microjensky per beam in the center. And we detect 2,483 counterparts to those 5,000 sources on the left. So we detect roughly 43% of the sources that are seen at 6 arcseconds. And of these sources, we find that 12% are extended and 88% actually still remain compact down to this high resolution. Now, to also convince you that we've actually imaged a contiguous area on the sky and that I'm not just showing you any postage stamps, here are some random area as seen by LOTS at 6 arcseconds. And if you then move to 0.3 arcseconds, the sky changes into this. And we can see that it gets a bit hard to visualize, but we can see the nice increase in detail that we get. And for this other part of the sky, can see these blobs at 6 arcseconds, and again the nice increase in detail that you get at 0.3 arcseconds. Some sources disappear because they're very diffuse, and some remain compact and are small points. And well, yeah, just some more cutouts because I like showing these pretty pictures, really showing the power that the ILT can give you. And so to reiterate finally back to this question at the beginning, why do we care about this? Well, first of all, obviously they're pretty pictures. But I also think that the large field of view of LOFAR is a really strong point for enabling blind surveying and population studies. So you won't have to worry about putting in a proposal for following up a specific source and convincing the allocation committee that you're actually able to detect this source. You can just observe a piece of the sky and get thousands of sources at once. And also at this resolution, we are approaching the typical size of sources in the microjensky regime, which is around 0.3, 0.4 arcsecond resolution. And this resolution is also very well matched to other telescopes such as eMerlin and the VLA, which will give a huge benefit for spectral studies and the likes. And with that, I would like to thank you for your attention. I'll take any questions if there are. So.
Thank you very much for a very nice talk, and you brought out the challenges of sub-arcsecond imaging and the exciting results very well. Yes, Joe, please ask your question.
Yeah, Frits, it's just an amazing image. I just wanted you to elaborate a little bit on saying only having 50% of the lot sources, because don't you have all the short baselines from in this? It's not like the difference between A configuration and D configuration with the VLA, right? You should have all the same spatial information, right? Or the way you're grouping the core stopping you from accessing the more diffuse emission?
No, you're absolutely right. So you're right. This is made with all the baselines included, except for some of the very shortest. So the information is actually there. I didn't put it in, but if you smooth these images back to like 6 arcsecond resolution, then all the diffuse emission in LOTS will pop back up, and you do detect this. So it's not so much a question that you're actually missing it, but it rapidly falls below the surface brightness sensitivity of this image.
Yeah, that's a really interesting way of thinking about it. And I think you should always reinforce that, because like a lot of people just assume more like a VLBI interpretation here. Depending on your science goal, right? You could smooth here and scale up, right? And
Yeah,
you would
definitely.
recover all those sources. Yeah, it's really cool stuff.
Thanks, Joe. Any more question for Fritz? If not, maybe I'll ask something very quick. So I'm really excited to see these amazing images. And do you have any plans for following up at very high frequencies with, say, VLA and ALMA, and get a very, very wide band spectrum and try to understand the properties, which has never been possible so far, because we didn't have such great high resolution images at lower frequencies?
So not specifically. There are some plans floating around to follow it up with eMerlin to make a resolution matched image as well. So yeah, no specific real plans, but ideas are floating around regarding that.
Okay, sure. Thanks. Stefan, please go ahead.
Yeah, just quickly, since John's on, how does your ionospheric correction scheme compare with what MWA does?
That is a good question. I must admit, I'm not aware of what MWA does.
Yeah, that is a very good question. I mean, it's very different because we have this enormously wide field of view, but a very compact instrument, whereas here you have a very wide field of view for this kind of work, but very, very small field of view compared to the MWA and this really extended instrument. So but both of us need to care about a very big, wide chunk of the ionosphere, hundreds of kilometers across. One of us because we've got a wide field of view, and one of us because we have a very wide instrument sitting beneath it. But how that actually translates into methodology, I don't think there's any overlap at all, to be honest, except to say that for both of us a sort of direction dependent approach is important. For the MWA, it really is just refractive shifts and your image looks like you know, looking at the bottom of a swimming pool with a few waves going over it. Whereas I guess for you, it's that's more at the station level, and so it's easier to think about in the visibility domain.
Yeah.
All right, thanks,
Yeah, I think
John.
that's
We have some extra time. Rick, you can also ask your question. Please go ahead.
Yeah, can you hear me?
yes.
Yeah, so these results, these are utterly spectacular results. Congratulations to all. The question is this is from the HBA. What is the prospects for similar kind of imaging with the LBA, with larger fields of view, lower sensitivity, and a smaller isochromatic patch?
Yeah, so Christian Groeneveld, also in Leiden, has done some experiments with LBA long baselines. And for now, LBA seems to be really difficult to get working on these long baselines. So he looked at a few bright 3C sources, but even at I think it was something like 20 Jansky level sources, it started already getting a little bit iffy and getting the calibration completely stable. Mm-hmm. So I'm not completely sure if we'll be able to do this with the LBA anytime soon.
Okay.
All right, thanks, Rick. So if there are no more questions, let's thank, or I'll thank Fritz on behalf of all of us. Thank you very much. And I again encourage you to please continue the discussion over the Slack channel. And the last talk of this session is by John Margren on MWA Phase II IPS survey. So John, you would like to share your slides? Yeah.
Hello, everyone. Apparently Zoom has quit on me, so I'll just, disappear in a second.
We're having some technical difficulties. We'll give John a minute or two to join again. Okay, I think he's back now. We've had a, yeah, there we go. Well,
Yes,
John's
good.
sharing, but we can't hear you, John, if you're speaking.
Okay, can you hear me now?
Yes, we can hear you now.
Yes.
Okay, can you see me? There's no
Yes.
black patches or anything?
We can see your slides, but we can't see you.
Okay, that's fine. I can, well, actually I might leave myself off because Zoom's already quit. Zoom's already crashed on me once, so let's not rock the boat. So let me get started without any further ado. My name is John Morgan. I'm a postdoc at Curtin University. For almost a decade now, I've been using the Murchison wide field array, and for many years, I've been using it to make interplanetary scintillation measurements. So I put in an abstract to talk about the first data release of our big IPS survey that we've been working on for a couple of years now. The SOC very kindly upgraded me to an invited talk. So I've, as befits an invited talk, I've tried to expand it out a little bit. So we now have the subtitle of Interplanetary Scintillation. What is it and why should you care? Because it's actually, and I'm very, very grateful to the SOC for giving me this time. It's a tricky subject to talk about and present science results in a normal conference talk, because it takes a good few minutes to actually explain to the other participants what interplanetary scintillation is. So I'm delighted to be able to take a little bit more time to give a little bit of context and hopefully convince you all, whether you're space weather people, of whom I know there's several online, or whether you're interested in more general galactic and extragalactic radio science, why this old neat trick from the 1960s has such relevance in this modern era of low frequency radio astronomy. So let's start by going right back to the discovery of IPS, interplanetary scintillation. So it's early 1964, and Margaret Clark, a PhD student at Cambridge, is completing her PhD studies with an astrometric study with a 1 kilometer baseline at I think about 150 megahertz of a number of 3C sources. She notes that they show these short timescale fluctuations, or at least a subset of sources do, that are compact, and that this increases with distance, increases with decreasing distance from the sun. And being something of an expert on the ionosphere herself, and a bit of an expert in, and rarely knowledgeable therefore about ionospheric scintillation, she realized that the fact that this was detected even on a kilometer baseline on these very short time scales pushed the velocity and the distance to the scattering screen out well beyond the Earth and its environs. And she speculated in her appendix to her PhD thesis that this may be due to solar coronal effects. She submitted her PhD thesis and headed off to Parkes in Australia. A month or two later, she was shocked to discover that Tony Hewish, who wasn't even her supervisor as it happens, had submitted a paper to Nature some 3 weeks after she submitted her PhD thesis with this discovery, without her on the paper, although he was gracious enough to thank Margaret Clark for pointing this out and undoing all of the observations and making the discovery and correctly interpreting it, although he didn't put that last bit in the paper. So, as many of you will know, IPS did then go on to have an indirect role in the discovery of pulsars, because The really exciting thing about IPS, particularly back in 1964, is that it allowed a way to identify compact, and by this we mean definitively sub-arcsecond structure, without building an interferometer capable of reaching that resolution, which in 1964 was barely technologically possible, and that resolution wasn't reached for another year or two. So this motivated the construction of the Cambridge IPS array, specifically to pick out these compact structures right at the time, around the time that quasars were being discovered. There was a very talented and tenacious PhD student, Jocelyn Bell, who managed to discover pulsars with it and won her PhD supervisor a Nobel Prize. That's a story that's reasonably well known in astrophysics, in radio astronomy, I guess. Less well known is that there were a few other highlights in IPS studies over the subsequent decades. So it never quite sort of played the hugely promising role that it might have in our increasing understanding of quasars and other compact radio sources, because very soon after it was discovered, interferometers moved to higher frequencies and longer baselines, including VLBI, and IPS became something of a niche for space weather studies, for which it's been, reasonably successful. But right back in 1965, Hewish, along with a PhD student, identified a very compact source in the Crab Nebula. It was difficult to explain its brightness temperature on the basis of synchrotron emission. And so this was, of course, although they didn't know it at the time, the Crab pulsar. Towards the end of the 1980s, Rickard and Cronin identified via IPS compact sources close to the galactic plane, where you would expect a distant source, extragalactic source, to be scattered broadened so that it wouldn't show IPS. They dubbed these sources Scintars. They came back with the VLA a year or so later and followed them up and realized they were mostly doubles and probably fairly boring radio galaxies that just weren't scattered because they were passing through a fairly clear line of sight. But there was one exception, which turned out to be the first ever millisecond pulsar discovered. So it was identified as a compact and very interesting and unusual source by IPS before it was discovered as a pulsar. Just a little unfortunate that they didn't quite manage to figure out that it was a pulsar by the IPS alone. Beautifully described by Pietro earlier, you can do multi-station IPS, which gives you extra information, particularly on the velocity of the scattering screen. And this approach was reapplied in the interstellar scintillation context to understand how IDV worked several decades later. And this is another thing that comes back. A lot of the people who made the great discoveries in interstellar scattering first cut their teeth on doing IPS work. And as I've mentioned already, galactic scattering is something that you can probe with IPS, and probably with low frequency VLBI as well, maybe even better. And I think this might end up being the real killer app for astrophysics for this work in the next few years. But the real success has been in remote sensing of the solar wind, and that's really the only kind of work that IPS has been used for in more recent times. So fast forwarding to the present day, there is a small but very close community of IPS enthusiasts all over the world. They use general purpose telescopes. They use IPS-specific telescopes, including the one with the largest collection area in the world, to do IPS. And the dream is that we can start to coordinate, do our work in near real time, and actually provide useful input to space weather forecasting. We're not quite there yet, but that's what we're all working towards. Anyway, back to low frequencies. So as we all know, as we're all here, H1 cosmology has led to a resurgence in low frequency radio astronomy. We have this suite of new instruments, and they are all beautiful instruments for doing IPS. Low frequencies is a good frequency to choose for IPS. As the solar wind moves away from the sun, it gets less dense. So you can choose your sweet spot depending on the level of scattering you want. And for LOFAR and MWA frequencies, 20 to 40 degrees solar elongation works quite well, which works brilliantly for the MWA because it means we can put the sun in the null of the primary beam. LOFAR is also an outstanding instrument for multi-station IPS. You can form these cross correlations between all of the baselines of your array, not full coherent phase stable cross correlations. This is simply taking light curves with a fraction of a second resolution and cross correlating their amplitudes and really map out different solar wind speeds along the line of sight in a huge amount of detail. Moving on to the MWA, so let's give you a bit of an idea of what this looks like. So this is a slightly speeded up movie of a small fraction of the middle of the MWA's primary beam, about 30 degrees from the sun. You can see some radio sources are twinkling, others are not, and the ones that are twinkling vary in different ways. Some of them are really switching on and off on timescales of a couple of seconds, and others are just wobbling around a little bit. And so we can take one of those interesting sources, zero in on that source's pixel and plot it in the time domain, and we get this, and the bottom shows power spectra at varying resolutions, and they show the characteristic shape of scintillation. So we can use that characteristic shape in the frequency domain to filter our time series lightly to accentuate the time scales where IPS is most prominent, and we can very, very cleanly make a map of what our variability is. So here we're swapping between the mean and the standard deviation of that filtered time series. You can see certain sources just completely vanish because they show no IPS, while others stay there, and those are our IPS sources, which you can characterize extremely accurately. It's very, very clean data. So before I dive into some of our science results, I thought I would just give you a bit of a philosophical overview of how approaching the compact sky from this direction has formed my sort of view of what we see. Having started with my PhD and first postdoc in widefield VLBI, similar to what Frits was talking about, but at higher frequencies, I know that widefield VLBI is hard, although Frits has demonstrated that it really is possible with LOFAR and modern computing infrastructure. IPS with the MWA is intrinsically wide field, and it really gives us a unique perspective on compact sources, I think, and this goes for Fritz's work as well, because you're seeing these compact sources in the context of all of the compact structure in the sky. Whereas at higher frequencies, people tend to see VLBI sources through a particular lens of these are the quasar type objects, these are the flat spectrum type objects. When you look at all the compact structure on that slightly larger scale than you get from higher frequency VLBI, hundreds of milliarcseconds rather than milliarcseconds, you see a lot more than just those little point-like quasars with a few little blobs coming out. And as Sarah White has pointed out, beaming is much less important than at higher frequencies. So our parent population is a little bit less biased in this particular sense. So a very, very quick whistle-stop talk of our work so far. So I work very closely with Rajan Chetri, another postdoc at Curtin. And in his first paper, we flattened out the solar elongation dependence of the scintillation index, and we invented this normalized scintillation index, where it is relative to the scintillation of a point-like source, which would be at 1.0. So we can then kind of divide it up into categories of strong, moderate, or weak, or non-scintillators. These are their SEDs, normalized by our observing frequency. The weak and non-scintillators are the majority at this frequency, and they all look like the majority of sources at this frequency, sort of steepish spectrum index minus 0.8 sources. The moderate scintillators are a little bit flatter. The very strong scintillators are a real mixed bag, everything from a typical steepish spectrum source to an inverted source to a peak source and everything else. So among those really compact sources, You get a 1-to-1-to-1 of flattish spectrum, steepish spectrum, and most importantly, perhaps the peaked spectrum sources. This is very different from the overall low frequency source population and very different from what you see in the compact source population at higher frequencies. And because we have this complete census of the compact source, we can do things like source counts, which is what Rajan did for his second paper. And there's a weak, well, actually a fairly significant difference between our observations and what's predicted by typical source models. Elaine Sadler, who's been a strong supporter of our work on this from pretty much from day one, has done some work as well looking at the infrared properties of our sources and shown that there's a sort of infrared correlation with redshift that are non-detection wise puts the source at a redshift of about 2.1 for these particular sources, which is about 40% of Joe's peak spectrum sources and a significant number of all of our compact sources. So this is well known. Compactness is a good quantum of information when you're looking for high redshift sources, and all of ours are at least moderately high redshift, or a lot of them are. So that was MWA Phase I, and all of the 5 papers we got from 2 5-minute observations. So roll on Phase II, a much better designed array for this work. Much less compromise goes into its layout. We can get beautiful, almost naturally weighted data with a perfectly Gaussian beam, and we've done a lot of work behind the scenes to improve our survey design and scheduling as well. So the gray points here are all of our observations through the first half of 2019. We track the sun, we do pointings all around the sun each day, and we track the sun as it moves across the ecliptic, and those magenta points are the ones that we've selected for our first data release. So we're massively oversampling the sky. Our beam's 30 degrees across. We deliberately tried to get overlap with the Northern Hemisphere for comparison with international LOFAR, and a general area around the galactic anticenter, as well as some of the well-known equatorial fields, which are well covered by FIRST and far infrared deeper surveys and so on. So in the interest of time, I'm going to run through this rather quickly. I'll just point out that because we're detecting variability and not the standard deviation of a Gaussian distribution and not its mean, the statistics work a little bit differently from what you might be used to. We use the standard deviation rather than the variance because the standard deviation is chi distributed, converges on a Gaussian much quicker than the much better known chi squared. But then we have to deconvolve our noise, our thermal noise, from the actual modulation, which is due to the IPS. And the way this works is that we can measure the location on the map where we have both the thermal noise and the IPS. We can measure off source and figure out the background level of variability due to the thermal noise. And both of these quantities have errors on them. And we're trying to figure out this smallest side of the triangle, if you like, from these two lengths. And that means, well, it's tricky. And if you sort of Taylor expand it, what you end up with is that the detection limit actually goes down with the 4th root of observing time, which is really annoying because we're not confusion limited, and it would be nice to be able to go really, really deep with this, but we can't. And that applies to any kind of combination, whether it's stacking of sources or whether it's stacking of images or mosaicing, in other words. So we don't mosaic, we keep our observations separate. We make measurements of every gleam source within the field of view for each of those 250 observations. And that means for an individual source, we end up with a very large number of measurements. And then we fit in this Gaussian regime. So we figure out the normalized scintillation index, which is most consistent with our data, has the lowest residuals, transforming our data so that our errors are Gaussian, essentially. And because of that funny sort of non-linearity, this is the chi-squared landscape for a strong source. Around the most likely value for the normalized scintillation index, it's a parabola. which is what you expect for the chi-squared. It's kind of a log likelihood type thing. But for an upper limit, you actually have a large range of values that are consistent with the level of scintillation that you see. So results. Caveat, the catalogue has been around in some form for about a year, but I've only recently completed it in exactly this form, as in the last few weeks and days. So there's about 40,000 gleam sources, which are within our survey area, and about 8,000 of those are definite, very strongly detected IPS sources. The vast majority of the rest, we can put some upper limit, or a useful informative upper limit on the level of IPS that we see. And as a function of gleam flux density, this is the histograms for those three different groups. The completely unconstrained ones is a very small number at very low flux densities. These are our upper limits, and a very interesting thing happens at 1 Jansky. At 1 Jansky, we get more IPS sources than non-IPS sources. So what does that mean? Let's plot it in a different way. Now we have the flux density against the normalized scintillation index here. And this red line crosses an NSI of 1 at about 100 millijanskis, and 0.01 NSI at 10 janskis. This reflects the fact that those two sources on that line in those two places have the same amount of complex flux. They both have 100 millijanskis of complex flux. So we have some degree of completeness along that line. And when we hit 1 Jansky, where we are at some level complete at about a 10% scintillation index, most of our sources show IPS. So you get a relatively uniform distribution of NSIs, broadly speaking. Details are a lot more complicated and flux density dependent. And so what we can say is that most 1 Jansky sources in gleam have a 10% compact component or thereabouts. And that's interesting to me, you know. There's a lot of, dare I say it, boring sources in gleam, but actually there seems to be some recent activity, at least recent and active enough to cause a hotspot to be present.
John, you have 4 minutes.
4 minutes, thank you. Okay, so a little bit of early science has been done, and some of it's even been published, even though we don't have the final catalogue paper out. So as well as Elaine's work, we have a separate high redshift radio galaxy group here at Curtin, and we have provided our IPS information to them on their high redshift candidates. And they are all remarkably similar. They are not as compact as Joe's peaked sources. These are peaked-ish sources, one of the main constraints for choosing these. And they all appear to have a compactness compatible with maybe 1 arcsecond size or something like that. Why they're so uniform and consistent, I'm really not quite sure. As Leigh talked about in her talk, we have done an in-depth comparison with International LOFAR, and that's appeared in their Calibrator survey paper, which we contributed to. We get this really beautiful agreement with their compact flux density versus our flux density. In terms of characterizing the source structure on sub-arcsecond scales, we've tried to do that, but we've kind of struggled. And the main reason is that a lot of the structure appears to be on much larger scales than the sort of scales that are probed by those international LOFAR baselines, which match so well with our IPS scales. Most of it is actually on somewhat larger scales. But if we pick those sources where the gleam flux density matches the shortest 100-kilometer LOFAR baseline visibility amplitudes, we are able to say, albeit with very large error bars, that our normalized scintillation index matches the sort of formally defined relationship between the scintillation index and source size with a circular Gaussian source morphology. We can go below this single number to characterize our sources, though, and that's because we've got these beautiful time series. We can form power spectra, and cutting it very short because I'm running out of time, the power spectrum of an IPS source is basically the source visibility amplitude squared multiplied by this concentric filter here. We're all in the visibility domain here. And that gives you, and then you integrate along one axis, which is defined by the solar wind velocity vector across the source. And that gives you the power spectrum. Now, if you've got a Gaussian source, well, it sucks to be you because it gives you a very boring power spectrum. But as Frits and Lei have shown, we don't have boring circular Gaussian sources. We've got all this beautiful structure. So here I've taken a VLBI image of 3C48, and I predicted its IPS power spectrum as we change the angle with which the solar wind goes across it, which of course will happen as the Earth moves around its orbit and the Earth-Sun source geometry changes. And you can see all of this rich structure in here, but this is a noiseless case. We wanted to understand, you know, could we still recover source information from the VLBI, from the IPS power spectrum with realistic noise? So the very first step to understanding this, we got a third-year student, Max Dmitriev, very talented guy. We had a very simple source model, just a 3-parameter double, extremely simplistic solar wind, just 2 parameters. We added realistic noise, and then we fitted to try and recover our original 5 parameters. And we were shocked at just how well it worked. Provided that the angle to the solar wind of the double is within, you know, 30, 40 degrees or so, you can recover some of these parameters to a 1% error. Now, I don't for 1 minute expect this to translate perfectly into the real world, but this is a really encouraging first step, especially for using single station IPS to figure out the velocity of the solar wind. I'm out of time now, but we of course want to apply this to real MWA data. We've been doing a lot of other interesting stuff, like applying the same technique to understand ionospheric scintillation. We've got our first scintillation measurement from ASCAP. Many thanks to Danica Scott and Rajan Chetri for that. So that's interesting as well. And my very last slide is just to give a very, very sneak preview of a very exciting result we've got, where when we try to predict the very, very noisy statistic, how compact a source is compared to what we would expect from its spectrum, its SED in the gleam band. It's a very noisy statistic for any individual source, but with enough sources, it gives you something meaningful. And if we plot the that statistic against H alpha intensity from a global sky map, we see that the sources get less compact as we increase the H alpha intensity, broadly in line with predictions of my colleague Paul Hancock. So watch this space for a lot more information on this, because I think this could be a real killer app for low frequency interferometry in the future, getting a handle on that most elusive of things, the ionized interstellar medium. So I'll leave it there. I hope you agree after my talk, there's a lot of exciting stuff going on, and that we have you know, continuing relevance alongside international LOFAR well into the SKA era. We're always looking for opportunities. We are very much limited by human resources, and please look out for our exciting results in the future. Thank you very much.
Thank you, John. Thank you for a very informative talk, and also putting a very nice historical perspective in IPS. Thank you very, very much. So the talk is open for questions. Please raise your hand if you have any questions. Yes, Christina, please go ahead.
Hey, John, that was a really interesting talk. So I was kind of surprised at first to hear that it's the hotspots on separation that are, you know, sources that have separations of an arcsecond or more that are responsible for the scintillation. If you were to do an IPS study at higher frequency, would you expect that to still be the case, or do you think the cores would contribute more?
So the cores definitely contribute at some level, and of course both the core and the hotspot are likely to be flatter spectrum than the extended emission. But absolutely, as you go to higher frequencies, the hotspots are going to contribute less, and the cores are going to contribute more. But yeah, trying to disentangle that is is really interesting, because then you can actually use these results to understand well, what we hope to do, what Rajan in particular is very keen to do, is to use this to understand duty cycles and timescales of activity with this more or less beam a sample that's not biased by beaming. But absolutely, as you go to higher frequencies, it's going to be cores more and more until you're really just left with the quasar-like objects.
Great, thank you.
All right, Joe, please go ahead.
Yeah, so it's kind of building on that question. I think the when MWA was turning on, right, everyone's like, well, 150 megahertz, lobe dominated. You're not going to see cores, yada, yada, yada. But I think Frits, maybe this is a question for Frits as well. You know, it'd be interesting to see, look at the core to lobe dominance of these things so we can interpret this IPS stuff. Because things greater than a Jansky at LOFAR, I noticed that the cores are as bright as a lot of the lobes, and still a lot of cases of these bright sources. So interpreting like whether this is the hotspot dominating or a core, I just don't think it's very simple for these really high flux density sources. Like I think what a back of the envelope calculation will get you. I don't know. Maybe Frits will disagree with me. Maybe I'm starting a discussion that could happen later, but that's something to think about. The other thing, John, I wanted to ask about was with finding pulsars. So one of the ideas with IPS, right? I know you identified a couple known pulsars, but particularly pulsars that or compact objects that the beam is not towards us, and maybe we're seeing some quiescent. You know, IPS would be able to pick out really easily. I don't know if you've got anything like that in your sample.
Yeah, I mean, the main reason we covered the galactic plane was to try to find pulsars, and this is something that people have played this game with low frequency data a few times, and we really hoped that with this compact information we would be the ones who could make it work, where, you know, very talented people like Tara Murphy and Martin Bell had failed to find pulsars in this way. So we came up with a bunch of candidates that were reasonably steep spectrum and very, very compact, and we followed them up with parks. And we have not definitively detected a pulsar. So at the moment we're sort of licking our wounds. We've got some VLBI time on those sources, LBA time, to try and figure out what they actually are, if they're not pulsars, or at least they're not pulsating, or they weren't on when Parkes was on. There's always a number of get out clause that could mean that this is a pulsar, even though you don't detect its pulsations. There's this idea of a pulsar that's spin axis is the emission is aligned with the spin axis pole, and so it's just always on or always off, and that this might be the only way to detect them. But as of yet, no luck. And one of the issues is that we simply, with the MWA, can't get down to flux densities where we're likely to discover something new. I mean, you can never rule it out. There are, you know, might have just switched on or got missed by the existing surveys. But with the SKA, this might be something where the IPS can fill in a gap, or at least provide a useful quantum of information to inform the more traditional searches and where to look.
Yeah, I guess, yeah, the flux density limit is the problem there. And maybe this is an SKA low kind of goal here, but they are steep spectrum, right? So I guess if you just do a back of the envelope calculation, I don't know, that will tell you, right? Because like,
yeah, and Parkes have just gone and discovered a whole bunch of new pulsars, and the brightest of those, I need to check again, but the brightest of those, I think we would detect.
Yeah.
So it's not inconceivable, but we haven't managed to make it work yet.
Okay, fingers crossed. Sounds good.
All right, thanks, Joe. Any more questions for John? If not, I would like to thank John for a very interesting talk. Thank you so much. And I would also like to thank all the speakers of this session, and I will encourage all of you to please continue discussing science about this session in the Slack channel, as well as gather down. Thank you so much. Thanks to all the speakers.